The purpose of this video is to answer the question, why feedback? You've worked pretty hard in this course, and you've come a fairly long way. We had a couple tests, and now we're approaching week 9 and dead week. And you probably wonder, what's it all about? Well, systems engineering is essentially putting complex systems, control systems together. Not necessarily exactly as we've done it, but certainly as pieces of a whole. So we hope that eventually you'll see some payoff in the work that you're putting in. So, one more time, why feedback? Well, our answer so far, and I hope you remember this, is to achieve stable task-related performance, which basically translates into a bandwidth under uncertainty, where we don't really know the plant, at reasonable cost. So we have multiple inputs, multiple outputs, and we have transfer function matrices in between, which the only division we've made in them is between the longitudinal modes and the lateral modes, and that's only for conventionally looking airplane. But basically, if you change through a SISO loop closure, if you do a SISO loop closure on any one of these loops, you will change all the modes, all the characteristic equations identically in the MIMO system. So if you close these single SISO loops in order to be stable through a SAS and a CAS, and you've got your stability, then you can be assured that the MIMO system is still stable. Of course, we're dealing with linear systems here. Now let me give you an actual example of how you would close these SISO loops in a MIMO system. This is a advanced fighter, an F-18, one of the earlier control implementations on the F-18. And here we can recognize a command loop for roll. Here's our aileron and our rudder loops. We recognize the rudder actuators, rudder and the aileron actuators. 20 over S plus 20, 25 over S plus 25. There's a delay here, and let's ignore this for now. We'll talk about this later this week. But your aileron and your rudders go into the airframe, and out come the outputs. And what we see here is that in the rudder loop, we have a SAS. In the rudder loop, we call this SAS a washout. And in the aileron loop, we also have a SAS. And in the aileron loop, we have a SAS. It's not only a gain of 0.3, but it's also a lead compensator. So, here's our problem. Can we design these inner loops so that the overall MIMO system outputs are still stable and we meet performance specifications that may exist for the rudder and for the aileron loops? And we might have disturbances that act in the forward loop here somewhere. And we might have noise. For example, we know our rates come from sensors. Our washout circuits and our rate sensors may have noise in them. So is it possible to design a system that attenuates disturbances, attenuates the noise, and is relatively insensitive to changes in plant parameters? You're asking an awful lot here. But the answer is, with Bode's theorem, or the Hurwitz criterion, is yes. This is probably the only time we'll talk about these criterion, other than me to mention many times that Bode and Hurwitz were geniuses. Let's see why this may be possible. We call this process of designing for good command following and disturbance rejection and bandwidth loop shaping. It came to me from a man named Peter Thompson, a Caltech graduate, who is a minor genius in his own right. He's written control programs, and last I know he works for Caltech. JPL. So, and system technology downtown in Hawthorne. Command following at low frequencies, we'll show you that this can happen when we have what's called high gain at low frequencies in the Bode plot for the variable that is being fed back. So if you want to control a variable, you feed it back and make sure you have high gain at low frequencies, and then you'll have good command following. We'll see that. But we also want disturbance rejection. If we have disturbance somewhere in this loop, we want to be able to reject that disturbance. So this also occurs if we have high gain at low frequency. So high gain at low frequency is not only going to give us good command following, that means it'll follow a step response, for example, with low error or no error, but it'll also have good disturbance rejection. It'll all be frequency dependent. Now, we might have sensor noise in our system if we have sensors or some noise injected into our output somehow, and that we're feeding back, and it becomes part of our control loop. So we want to reject that sensor noise, but we want to do that at high frequencies. And this is the key. We're doing one thing at low frequencies and another at high frequencies. And the separation of the Bode plot allows us to do that. Finally, we're going to want adequate bandwidth. When we close the loop on this open loop system, we want adequate bandwidth. And we know that the closed loop bandwidth is closely predicted by the open loop crossover. So we want to have decent phase margin and gain margin, at least for certainly phase margin, in the presence of time delay, or what we call delay margin, and I'll define this later on in the week also. So this chart kind of defines the rest of our time working together. We're going to build lag compensators and integral lag compensators to give us high gain at low frequency, but will not affect the higher frequency part of the curve. Then we'll build lead compensators and washouts possibly that will give us good crossover frequency and good phase margin, but they won't affect the low frequency part of the curve. So you can design to meet these objectives separately in different frequency regions. That's the genius of the Bode theorem. And then, of course, we'll want to roll off past crossover. We'll want the feedback to stop working. So we'll want to roll this off at high frequencies. And I'll show you how to do that so that you get good noise rejection and robust stability at high frequency. So let's summarize. This is from Peter Thompson's book on his control book, CC. At low frequencies, for good command following, disturbance rejection, and robust performance, we can actually think of this system working for any plant if we have good low frequency, high gain performance at low frequencies. This is where feedback is going to work. Feedback tends to stop working at crossover, where the log of the output equals the input, 0 dB. This is a good predictor of the bandwidth of the system, which is a primary specification. Finally, our high gain region, we want to reject sensor noise, so we want lots of roll-off going many powers of 10 below 10 to the minus 3, 10 to the minus 4, to reject any sensor noise which might be out here. Now let me take a minute to show you why this works so beautifully in our situation. Here we have a linear system. The system has to be linear because we're going to use what's called superposition. We're going to take these inputs one at a time and set the other inputs equal to 0. And when we do that, we'll get a response y to each of the inputs with the other one set equal to 0. So let's take example y to our command input. Here's the solution that Peter Thompson gives us for the 3 different inputs up here at the top. Now this first one, if we set these other two, disturbance and noise, equal to 0, gives us our command performance. Can you see if G is made very large? If we make G very large by, for example, closing the root locus gain on it, that will dominate the 1. And then you're going to have G over G, or Y commanded equals the input. The output equals the output commanded. So that's going to give you good command response and good disturbance rejection over a low frequency range. High gain at low frequency. If we look in the frequency domain and put S equals J omega, then we'll see that if we can make the magnitude of G of J omega much, much greater than 1, then we're going to have output equal to input. Now once again, we're talking about this part of the region right here. So we want high gain at low frequency. That gives us low steady state error or no steady state error and good performance as long as we can get the bandwidth out here where we need it for our specification. Now let's look now at the disturbance, which operates somewhere in the forward loop here. Turbulence, whatever, some kind of disturbance is going to hit our system. If you take the transfer function for the disturbance and set the other two equal to 0 using superposition, you get 1 over 1 plus GH. Again, if you make G very large, then you can see that the output's going to go to 0 from the disturbance. That's exactly what we want. We want the output disturbance rejected in the output. And we see that this is going to happen if we make G very large. So far, everything is looking good. We got good command response. Y equals in the steady state equals the commanded Y in the steady state. And we have good disturbance rejection. One thing to point out in this transfer function, if you read through here, is the magnitude is infinite at omega equals 0 if G contains an integrator. We have a K over S. If S equals J omega and omega goes to 0, you get an infinite. So that means that you're going to have no error if you have an integrator in your open loop transfer function forward path. Okay? There is 0 steady state error to a step input if G contains an integrator. So you can also show that there's 0 steady state error of a ramp input if you have a double integrator, and on and on and on. The problem with adding these integrators, of course, as we know from class, is that you're going to be adding minus 90 degrees of phase every time you add an integrator. So that could be a serious problem. Finally, let's consider the sensor noise. If we have like your lab 2 gyro is put into the system and we're feeding back a rate, or if we have a washout circuit that's differentiating a signal proportional to its rate, then we could have noise, and there could be noise from other sources as well. So let's see how this is going to affect our system. Going back to the block diagram, we see that the noise would occur somewhere after the output. And if we calculate the transfer function, we get G over 1 plus GH again. But now we want this to be small. So good sensor noise rejection cannot occur at low frequencies, right? It must occur at another frequency range, usually low gain at high frequency. So if we had low gain somehow here at high frequency, then you'll see that the low gain, the 1 will dominate the G, and of course then I'll just have G as the transfer function for the closed loop. In other words, the open loop and the closed loop will be the same, and since it's going to 0, the magnitude is going to 0, I will attenuate the noise. So command and disturbance rejections are achievable and achieved by having high gain at low frequency, and good sensor noise rejection is achieved by low gain at high frequencies. So returning to what we call our loop shaping diagram, we somehow have to design a system that's going to have very low gain here at high frequencies after crossover, and yet we need to push the crossover high enough to meet the specification for performance, where our crossover predicts the bandwidth that's acceptable. And then we want high gain at low frequency so that we have good disturbance rejection and command response. Here's the beautiful thing about loop shaping. For most physical systems, this is achievable. Now this may be the only time until you take advanced control courses that you'll see why this is achievable, but it comes from the Bode theorem, or the Hurwitz criterion, which basically sets this identity as a necessity for a control system. And the practical implications of this relationship is that the integral is positive over a frequency range where 1 plus g omega has a gain greater than 1, but it must be compensated by a frequency region where the gain is less than 1. In other words, if we have a low gain region to arbitrarily higher frequencies, but a roll-off must eventually occur. Now, Laplace transform, S equals j omega, satisfies this if you have 2 more poles than zeros. Well, this is great because the bandwidth of a closed loop system, which is predicted by the cutoff frequency or of the open loop system, it's the frequency where the closed loop transfer function is approximately half, or 3 dB. The cutoff frequency is approximated by the crossover frequency, where g of j omega of the open loop equals 1. Therefore, we can easily see the bandwidth prediction on a Bode plot of the open loop system. The bandwidth is important because it's inversely proportional to the rise time. The higher the bandwidth, the shorter the rise time. And higher bandwidths have faster speeds of response. That's where your specification normally resides. A good classical control design will have a loop transfer function which approximates k over s, or omega c over s, over the frequency range near the bandwidth. This is the key thing. If we have a k over s at crossover frequency, So if our slope in this area of crossover is about 20 dB minus 20 dB per decade, then in the minimum phase system, the angle will tend to be minus 90 degrees. It'll tend towards minus 90 degrees, which will give us a phase margin of nearly 90 degrees, a very good prediction of robustness. And there you have it. So our goal when we're doing loop shaping will be to get adequate performance by using lead compensation or washout, which will give us a good phase margin at adequate performance. Then we'll want to build low frequency, possibly adding integrators or integral lag compensators at the low region to give us good command following and good disturbance rejection. And we have to get rid of the angle that comes with an integration of minus 90 degrees. We have to get rid of that angle before we get to crossover. So that's what our lag compensator's job is going to be, and we're going to do that this week. The high frequency region here, you just, after crossover, you just want to roll this off rapidly. And this is done by adding, say, 1 over s plus 50 quantity cubed. So you can just add filters, high frequency filters, which will filter out all the high frequency noise you want. But being careful that you remember that the angles from those high frequency filters start an order of magnitude. They start decaying an order of magnitude before the break frequencies. So if that order of, say it had a break frequency of 1 over s plus 50 cubed, well, that angle decay is going to start at omega 5. If it's 1 over s plus 50, then at 5, the angle decay is going to start, and it's going to affect my phase margin. But this is our task before us this week, to take our system, whatever that system might be, aircraft in this case, or a rocket, or a satellite, and design SAS loops, stabilization loops, which pretty much always operate. And we can use either washout circuits or rate sensors to get those SAS operating and stabilize our system. Then we'll close as needed, as desired. We'll close outer loops on these systems, and that outer loop closure will allow us to do command following. And if you do the design correctly, in other words, if I do my loop shaping on this SISO loop correctly, inner loop and outer loop SISO correctly, then the change in the MIMO system, the multi-input, multi-output system, will have the same characteristic equation as the SISO systems. The zeros for the transfer functions relating the outputs to the zeros, those zeros will tend to be transmitted from loop closure to loop closure. We call those transmission zeros. Well, I hope you see the purpose of feedback. Here is kind of a summary of what was presented in the class in a prior year, so you can look at it, and it kind of shows you how you want to close these loops with disturbance and noise and command following, so that you get high gain at low frequency for good command following, because that's going to make Y and R the same. That high gain at low frequency is going to eliminate the disturbance. But then at high frequencies, if the OLTF has gotten very small, then the 1 will dominate and you'll cancel out the noise. This ends this video. You can go to Amazon to get a prize now, a SISO tool for everyone.